The universe has the same temperature everywhere you look. This breaks every rule of physics. Most people assume space varies randomly across different regions. Wrong. When scientists measure ancient heat signals from space, they find identical temperatures spanning impossible distances. Tonight we're discovering how the universe solved this problem in its first fraction of a second. We'll trace the evidence that led to one of physics' wildest ideas. Before we explore this cosmic puzzle, drop a comment about where you're listening from. If you enjoy these deep space mysteries, consider subscribing. These late-night physics journeys are meant to be shared. Two engineers just wanted to fix their radio antenna. The year was 1965. They worked at Bell Labs, a famous research company. They kept hearing annoying static that wouldn't go away. That noise changed everything. They'd accidentally discovered heat left over from when the universe was born. Scientists call this the cosmic microwave background. Think of it as the universe's oldest baby photo. When other scientists mapped these heat signals across the entire sky, they found something impossible. Every direction shows nearly identical temperatures. We're talking about differences smaller than a snowflake. Here's the problem that makes no sense. These regions lie on completely opposite sides of space. Nothing could have traveled between them to share information. Yet somehow they maintain perfect coordination. You're looking at evidence from when the universe first became transparent. Before this moment, space was so hot and dense that light couldn't travel anywhere. This discovery shows us that moment when everything cleared up. Nothing in the universe travels faster than light. Not signals, not heat, not any kind of information. This speed limit creates what scientists call the horizon problem. Picture the early universe when it was just 380,000 years old. That's incredibly young by cosmic standards. Light could only travel that same distance in any direction during that time. But those heat signals we discovered show us regions separated by vastly larger distances. They should be completely isolated from each other, like two islands that never had boats traveling between them. The math becomes brutally clear. Opposite edges of our visible universe were separated by distances that light couldn't cross in time. They should display completely random temperatures. Instead, they agree perfectly. This coordination spans roughly 100,000 separate regions that should have evolved on their own. Without some mechanism connecting them, this uniformity violates the basic rules of cause and effect. Scientists expected cosmic chaos when they first studied deep space. Random hot spots, cold zones, wildly different conditions everywhere you looked. What they found instead shocked the physics community. Every patch of space they measured showed identical properties. Not just temperature, but density, pressure, and energy levels too. This discovery goes far beyond the heat signals we talked about. We're seeing identical physical conditions across regions that never had any contact with each other. It's like finding identical snowflakes in places where no weather patterns could have connected them. The measurements keep getting more precise, and the mystery only deepens. Modern telescopes can detect variations as small as parts per million, yet the uniformity remains almost perfect across impossible distances. This level of coordination suggests something extraordinary happened in the universe's earliest moments. Some process must have synchronized everything before normal physics took over. Imagine trying to balance a pencil on its tip. That's essentially what our universe has accomplished with its geometry. Space can be curved in different ways, and just like surfaces can be curved, it could bow outward like a sphere, curve inward like a saddle, or lie perfectly flat like a table. Scientists call this the flatness problem. Our universe chose the most unlikely option. It's so close to perfectly flat that it defies explanation. Any tiny deviation from this perfect balance would have caused the universe to either collapse immediately or expand so fast that nothing could ever form. The precision required is mind-boggling. We're talking about fine-tuning that makes balancing that pencil look easy. 1 part in a trillion wouldn't be accurate enough. This perfect flatness extends across every region of space we can observe. It's as if someone set up the entire universe with a cosmic level to make sure everything stayed perfectly balanced. Advanced physics theories predict that the early universe should have created exotic particles. Scientists call these magnetic monopoles. Think of them as magnets with only one pole instead of the usual north and south. These particles should be everywhere. The same conditions that created normal matter should have created massive quantities of these strange objects. They should be as common as hydrogen atoms. But we've never found a single one. Decades of searching with the most sensitive detectors have turned up nothing. It's like predicting that every forest should be full of unicorns, then discovering that no forest anywhere contains even one. This absence becomes even more mysterious when you consider the physics involved. The grand unified theories that explain most of particle physics require these objects to exist. Without them, our understanding of fundamental forces breaks down. The universe somehow managed to avoid creating these predicted particles entirely. This suggests that something dramatic happened in the early universe that prevented their formation. Our universe needed incredibly specific starting conditions to become what we see today. Scientists call this the initial conditions problem. Think about throwing darts at a dartboard from across a football field while blindfolded. Now imagine that the bullseye is 1,000 times smaller. That's the level of precision required for our universe to work. The density had to be exactly right. Too high, and everything would have collapsed into black holes immediately. Too low, and no stars or galaxies could ever have formed. The margin for error was essentially zero. The expansion rate needed identical precision, a tiny bit faster, and matter would have spread out too quickly for gravity to work. A tiny bit slower, and everything would have crunched back together in moments. Every fundamental constant in physics had to fall within incredibly narrow ranges. Change any one of them by a fraction of a percent, and the universe becomes lifeless and empty. The Big Bang Theory explains most of what we observe about the universe. It predicts the existence of cosmic background radiation, the abundance of light elements, and the expansion of space itself. But this successful theory hits a wall when we ask certain questions. It can't explain why the universe looks so uniform. It can't account for the perfect flatness we observe. It can't tell us why exotic particles are missing. These aren't small problems that future research might solve. They're fundamental gaps that challenge the theory's core assumptions. It's like having a map that accurately shows every street in your city, but completely fails to show why all the buildings look identical. Scientists call these the horizon problem, the flatness problem, and the monopole problem. Each one suggests that something crucial is missing from our understanding. The standard Big Bang model works perfectly for everything after the first fraction of a second. But that earliest moment remains completely mysterious. The forces that govern our universe appear to be fine-tuned for the existence of life. This creates what scientists call the fine-tuning problem. Consider the electromagnetic force that holds atoms together. If it were slightly stronger, stars couldn't burn hydrogen. If it were slightly weaker, atoms couldn't form complex molecules. Either way, no chemistry and no life. The strong nuclear force faces the same precision requirement. A small increase would make all hydrogen turn into helium immediately. A small decrease would prevent any elements heavier than hydrogen from forming. Even gravity follows this pattern. Slightly stronger, and stars would burn out before life could evolve. Slightly weaker, and stars couldn't form at all. These perfect values appear to be pure coincidence. There's no known physical reason why the constants should take exactly the values needed for complexity in life. Quantum mechanics predicts that empty space isn't actually empty. It should be filled with energy from particle pairs constantly appearing and disappearing. Scientists can calculate how much energy this quantum vacuum should contain. The number they get is enormous. It should be strong enough to curve space-time dramatically and dominate the universe's expansion. But when astronomers measure the actual energy density of empty space, they find something completely different. The real value is smaller than the predicted value by a factor that requires 120 zeros. This represents the worst prediction in the history of science. It's like calculating that your coffee cup should weigh as much as a mountain, then discovering it weighs exactly what you'd expect from a coffee cup. This cosmological constant problem suggests that something fundamental is missing from our understanding of quantum mechanics and gravity. The cosmic background radiation shows us a universe that was incredibly smooth and uniform. Variations in density were tiny, less than 1 part in 100,000. Yet today's universe is filled with dramatic structures. Galaxies cluster into groups. Those groups form superclusters. Between them lie vast empty voids where almost nothing exists. This creates a paradox that standard cosmology struggles to explain. How did such tiny variations grow into such dramatic structures in the time available? Gravity can amplify small differences, but not nearly fast enough to explain what we observe. The universe simply hasn't existed long enough for such small seeds to grow into such large trees. Computer simulations of structure formation consistently show that something extra was needed. Some additional process must have enhanced the growth of cosmic structures. By the late 1970s, cosmologists faced a crisis. Their best theories couldn't explain the most basic features of the universe they observed. The problems weren't going away with better measurements. If anything, more precise observations made the puzzles even more challenging. The universe's uniformity, flatness, and missing particles demanded explanations that existing physics couldn't provide. Some scientists began proposing radical solutions. Maybe the Big Bang Theory was fundamentally wrong. Maybe we needed completely new laws of physics. Maybe our observations were somehow misleading us. Others suggested that multiple mechanisms might work together to solve different problems. But this approach felt unsatisfying, like explaining a symphony by listing every individual note. What cosmology needed was a single, elegant solution that could address all these problems at once. The search for this revolutionary mechanism would lead to one of the most extraordinary ideas in physics. All these problems pointed toward the same conclusion. Something extraordinary must have happened in the universe's earliest moments. The evidence suggested a period when normal physics temporarily stopped working. A time when space itself behaved in ways that seem impossible under ordinary circumstances. This mysterious epoch would need to explain perfect temperature coordination, across disconnected regions. It would need to account for the universe's precise flatness and the absence of exotic particles. Most importantly, it would need to set up the initial conditions that allowed everything else to develop. The entire history of cosmic evolution seemed to depend on events that occurred in the first tiny fraction of a second. The stage was set for a revolutionary proposal, an idea so radical that it would challenge our most basic assumptions about space, time, and the nature of reality itself. The solution would be called cosmic inflation. How far can light travel in 13.8 billion years? Scientists can calculate this distance exactly. It's called the observable horizon. Light moves at the fastest possible speed in the universe. Nothing can go quicker. So this horizon represents the absolute maximum distance that any signal or influence could have traveled since the Big Bang. But here's where the math becomes devastating. When you calculate how far apart different regions of space were in the early universe, the numbers don't work. Regions showing identical temperatures were separated by distances far exceeding what light could cross. The cosmic microwave background shows us regions that are 90 times farther apart than the horizon distance allows. These areas should never have been able to communicate with each other. This mathematical impossibility forces us to conclude that standard Big Bang theory is missing something crucial. Picture two people standing on opposite sides of a football stadium. Now imagine they need to coordinate their actions perfectly, but they can't see each other, hear each other, or send any signals. This represents the situation in our early universe. Different regions of space had no physical way to exchange information or influence each other. Scientists call this the causal connection problem. In physics, nothing can influence anything else without some form of contact or signal. This principle forms the foundation of how cause and effect work. Yet the cosmic microwave background shows perfect coordination between regions that had zero causal contact. It's like those two people in the stadium somehow performing identical actions despite having no way to communicate. The early universe achieved impossible coordination across regions that physics says should be completely independent. The universe walks on a knife's edge between two forms of cosmic death. Too much matter and gravity wins. Everything collapses back into a point. Too little matter and expansion wins. Everything spreads apart so fast that no structures can form. Scientists call the boundary between these fates the critical density. Our universe sits incredibly close to this exact boundary value. The precision required defies belief. We're talking about accuracy to within one part in a trillion. Imagine trying to balance a pencil on its tip while riding a bicycle during an earthquake. Any tiny deviation from this critical value would have ended our universe almost immediately. Either instant collapse or runaway expansion with no stars, no planets, no life. The Big Bang theory cannot explain why the universe chose this impossibly precise density value. Space can be curved in three different ways. It can bow outward like the surface of a sphere. It can curve inward like a saddle shape. Or it can lie perfectly flat like a tabletop. Our universe chose the least likely option. Measurements show that space curvature is incredibly close to perfectly flat. Scientists call this value the curvature parameter, and it sits almost exactly at 0. This flatness becomes even more mysterious when you consider the alternatives. Any slight curve in either direction would grow dramatically over time. A slightly positive curve would cause rapid collapse. A slightly negative curve would prevent any structure formation. The universe somehow selected the one geometry that allows complexity to develop. This represents another impossible coincidence that standard cosmology cannot explain. Space geometry appears to have been fine-tuned with incredible precision from the very beginning. The early universe went through dramatic phase transitions as it cooled down. Think of water freezing into ice, but much more extreme. These transitions should have created permanent scars in the fabric of space itself. Scientists predict several types of cosmic defects from these transitions. Cosmic strings should stretch across the universe like cracks in broken glass. Domain walls should divide space into separate regions. Monopoles should exist as isolated magnetic poles. We've searched the sky extensively for these predicted defects. Advanced telescopes should easily detect their gravitational effects and electromagnetic signatures. The searches have found nothing. This absence creates a major problem for our understanding of phase transitions in the early universe. The physics that explains everything else demands these defects should exist everywhere. The universe appears to have undergone phase transitions without leaving the expected permanent marks. Astronomers can measure the age of stars by studying their light and composition. The oldest stars in our galaxy appear to be roughly 12 to 13 billion years old. But early measurements of the universe's expansion suggested it was only 10 billion years old. This created an obvious paradox. How can stars be older than the universe that contains them? Modern measurements have resolved this specific contradiction by showing the universe is actually 13.8 billion years old. But the underlying problem remains. The timeline for cosmic evolution appears uncomfortably tight. There barely seems to be enough time for all the complex processes we observe. Star formation, galaxy assembly, and chemical evolution all had to happen on compressed timescales. This age paradox highlights how finely balanced the cosmic timeline appears to be. The early universe started in an incredibly organized state. All matter and energy were distributed smoothly and uniformly. This represents a condition of very low entropy. Entropy measures disorder and chaos in any system. The second law of thermodynamics states that entropy always increases over time. Order naturally transforms into disorder, never the reverse. This creates a fundamental puzzle about cosmic origins. How did the universe begin in such a highly organized state? Random processes should have produced maximum chaos from the start. It's like finding a perfectly organized library after an explosion. The natural expectation would be scattered books and debris everywhere, not neat rows of properly shelved volumes. Standard Big Bang theory simply assumes this initial low entropy without explaining how such organization could arise naturally. The Big Bang should have produced equal amounts of matter and antimatter. These two types of particles annihilate each other completely when they meet, releasing pure energy. If the early universe contained equal amounts, everything should have annihilated. The result would be a universe filled only with light, containing no atoms, no stars, and no planets. Yet we exist in a universe made almost entirely of matter. Antimatter appears only in tiny quantities created by high-energy processes. This represents a massive asymmetry that requires explanation. The standard model of particle physics allows only tiny amounts of matter-antimatter asymmetry. The predicted imbalance falls far short of what we observe. This baryon asymmetry problem suggests that unknown physics operated in the early universe to create the matter dominance we see today. Modern telescopes can see galaxies that formed when the universe was less than 1 billion years old. These early galaxies appear surprisingly mature and well organized. Standard models of structure formation predict a much slower process. Small density variations should gradually grow under gravity's influence over many billions of years. But the observed timeline appears compressed. Massive galaxies and galaxy clusters seem to have assembled much faster than our models predict. This creates a serious problem for understanding cosmic evolution. Either our models of structure formation are wrong, or something additional accelerated the process. The universe appears to have built complex structures on timescales that challenge our understanding of gravitational assembly. The Big Bang theory predicts that the universe began at a point of infinite density and temperature. Mathematicians call this a singularity. At this point, all known laws of physics break down completely. Density becomes infinite. Temperature becomes infinite. Space and time lose all meaning. This represents a fundamental failure of our physical theories. Science cannot describe or predict what happens at a singularity. It's like having a mathematical equation that suddenly starts dividing by zero. The singularity problem reveals that Big Bang theory hits a wall at the most crucial moment. It cannot explain the actual origin of space, time, matter, and energy. This mathematical breakdown suggests that our current understanding of cosmic origins is fundamentally incomplete. Space can grow. This isn't science fiction. Einstein's equations allow the fabric of space itself to stretch and expand. But imagine space expanding so fast that it doubles in size every tiny fraction of a second. We're talking about growth rates that make explosives seem slow by comparison. Scientists call this exponential expansion. It means the universe doesn't just grow steadily. It grows faster and faster, doubling and redoubling at incredible speed. During this brief period, a region smaller than an atom could expand to the size of a grapefruit in less than a blink. Then that grapefruit-sized region would expand to the size of our solar system. This exponential growth represents the most dramatic transformation in cosmic history. Alan Guth was a young physicist struggling with cosmic puzzles in 1980. He worked at Stanford University, trying to understand why the universe looked so uniform and flat. One December evening, Guth had a revolutionary idea. What if the early universe underwent a period of incredibly rapid expansion? What if space itself inflated like a balloon being blown up at impossible speed? He called this process cosmic inflation. The idea seemed crazy at first. Nothing in known physics suggested that space could expand so dramatically. But when Guth worked through the mathematics, something amazing happened. This single mechanism solved multiple cosmic problems at once. The horizon problem, the flatness problem, and the monopole problem all disappeared. Guth's proposal would transform our understanding of the universe's origin story. Energy can get trapped in unusual states. Think of a ball stuck on a hill instead of rolling down to the bottom. Scientists call this higher energy state a false vacuum. This trapped energy creates something extraordinary. Instead of behaving like normal matter, it acts like a repulsive force. It pushes space apart rather than pulling things together through gravity. The false vacuum state contains enormous amounts of stored energy. This energy doesn't clump into particles or radiate away as light. Instead, it remains perfectly smooth and uniform throughout space. When space contains this type of energy, Einstein's equations demand exponential expansion. The false vacuum literally inflates the universe at incredible rates. This mechanism provides the driving force behind cosmic inflation. Imagine an invisible field that exists everywhere in the universe. This field has the same strength and properties at every point in space. Scientists call this a scalar field. Unlike the electromagnetic field that creates light or gravitational field that creates attraction, this scalar field creates repulsion. It pushes space apart rather than pulling things together. The scalar field responsible for inflation is called the inflaton. This field carries enormous energy density. Its energy doesn't vary from place to place, creating perfectly uniform conditions throughout space. When the inflaton field sits in its high energy state, it drives exponential expansion. The field's energy acts like a cosmic motor, inflating space at tremendous rates. This inflaton field represents the engine behind cosmic inflation. Einstein discovered that empty space can have its own energy density. This vacuum energy creates what physicists call the cosmological constant effect. Normal matter and energy create gravitational attraction. They pull things together. But vacuum energy behaves completely differently. It creates gravitational repulsion instead of attraction. This repulsive effect becomes stronger as space expands. More space means more vacuum energy, which creates even more repulsion. The process feeds on itself, accelerating the expansion. During inflation, this vacuum energy dominated everything else in the universe. Its repulsive effect overwhelmed all other forces, driving exponential expansion of space itself. The cosmological constant effect transforms empty space into the universe's most powerful expansive force. Before inflation, different regions of the early universe were close enough to communicate. Light signals could travel between them, allowing them to reach the same temperature and density. Then inflation began. Space expanded so rapidly that these connected regions got stretched to enormous distances. Areas that were once neighbors became separated by vast cosmic scales. This process is called horizon stretching. Regions that could once exchange information suddenly found themselves isolated by the expanding space between them. But here's the crucial point. These regions retained the identical properties they had when they were still connected. Their temperatures, densities, and other characteristics remained perfectly coordinated. Horizon stretching explains why distant parts of our universe show identical properties despite being unable to communicate today. Einstein's field equations describe how matter and energy curve space-time. These equations allow for many different solutions, depending on what type of matter and energy you include. One particular solution involves exponential expansion of space. When you include vacuum energy with repulsive properties, the equations predict runaway growth of spatial dimensions. This exponential solution represents a perfectly valid mathematical answer to Einstein's equations. The physics is completely consistent with general relativity. Einstein himself never considered this possibility because he didn't know about vacuum energy states that could drive such expansion. The concept emerged decades after his original work. The exponential solution provides the mathematical foundation for understanding cosmic inflation. During inflation, the universe doubled in size repeatedly, but the time scale involved defies human comprehension. Scientists can calculate exactly how long each doubling took. The answer is roughly 10 to the minus 37 seconds. That's a decimal point followed by 36 zeros and then a 1. To put this in perspective, light can only travel about 10 to the minus 29 meters in this time. That's much smaller than the nucleus of an atom. Yet in this impossibly brief moment, the entire universe doubled in size. Then it doubled again, and again, This process repeated dozens of times in the first fraction of a second. The doubling time during inflation represents the fastest transformation in cosmic history. Imagine inflating a balloon to enormous size. The surface starts out curved, but as the balloon grows bigger, any small patch becomes flatter and flatter. Cosmic inflation works the same way with space itself. The universe might have started with significant curvature, but exponential expansion stretched this curvature until it became negligible. This flattening mechanism solves the flatness problem automatically. You don't need to fine-tune the initial curvature to incredibly precise values. Inflation flattens any starting curvature naturally. The process works like cosmic ironing. Exponential expansion smooths out wrinkles in space-time geometry, leaving behind the flat universe we observe today. Space curvature gets diluted to undetectable levels by the inflationary stretching. The early universe should have been filled with exotic particles, magnetic monopoles, cosmic strings, and other strange objects predicted by advanced physics theories. But inflation provides a cosmic cleaning service. The exponential expansion dilutes the density of these particles to essentially zero. Think of adding one drop of ink to a glass of water, then magically expanding that glass to the size of an ocean. The ink becomes so diluted that you can't detect it anywhere. Inflation does the same thing to unwanted particles. It spreads them across such vast volumes that their density becomes negligible. The universe effectively becomes empty of these exotic relics. This dilution mechanism explains why we don't observe the strange particles that early universe physics predicts. Inflation couldn't continue forever. At some point, this period of exponential expansion had to end and transition into the normal cosmic evolution we understand. Scientists call this transition the graceful exit problem. How does inflation stop in a way that creates the hot, dense conditions needed for Big Bang nucleosynthesis? The solution involves the inflaton field rolling down from its high-energy state to a lower-energy configuration. This transition releases the stored vacuum energy as normal particles and radiation. The process creates exactly the hot, dense universe that standard Big Bang theory requires. Inflation sets up the initial conditions perfectly for everything that follows. This graceful exit connects the inflationary epoch seamlessly to the conventional cosmic timeline. Inflation makes specific, testable predictions about what we should observe in the universe today. These predictions can be checked against real astronomical data. The theory predicts nearly scale-invariant density fluctuations in the cosmic microwave background. It predicts specific patterns in the temperature variations across the sky. Inflation also predicts that the universe should be incredibly close to perfectly flat. It predicts the absence of exotic relics like magnetic monopoles. Most remarkably, inflation predicts the existence of primordial gravitational waves. These ripples in space-time should create specific patterns in the polarization of cosmic background radiation. These testable predictions transform inflation from wild speculation into legitimate scientific theory that can be verified or refuted by observation. How do you measure the size of the entire universe? Scientists use something called the scale factor. Think of it as a cosmic ruler that tracks how much space has expanded over time. During inflation, this scale factor follows an exponential pattern. Instead of growing steadily, it grows faster and faster. The mathematical function looks like a rocket ship taking off, not a gentle slope. This exponential growth means the universe doesn't just get bigger, it gets bigger at an accelerating rate each moment. space expands faster than the moment before. The scale factor during inflation increases by enormous amounts in incredibly short time periods. We're talking about growth rates that make explosions seem sluggish by comparison. This mathematical function captures the most dramatic expansion in cosmic history. Normal expansion slows down over time. When you throw a ball up, it starts fast, but gravity gradually slows it down. The universe should behave the same way. But during inflation, something extraordinary happens. The expansion rate stays almost perfectly constant. Scientists call this the Hubble parameter, and it barely changes during the inflationary period. This constant expansion rate creates sustained acceleration. Instead of slowing down like normal expansion, space keeps expanding at the same breakneck pace throughout inflation. Think of it like a car that maintains maximum acceleration for an extended period. The speed keeps increasing, but the acceleration itself stays constant. This steady Hubble parameter drives the exponential growth that characterizes cosmic inflation. Einstein's equations allow for different types of curved spacetime. One particular solution involves uniform vacuum energy spread throughout space. Scientists call this de Sitter spacetime. In de Sitter spacetime, the vacuum energy density remains perfectly constant everywhere. This creates a very specific type of geometry that's unlike anything we experience in everyday life. This special geometry has a crucial property. It naturally produces exponential expansion. The constant vacuum energy acts like a cosmic engine, driving space to inflate at tremendous rates. Willem de Sitter discovered this solution to Einstein's equations in 1917. He had no idea he was describing the physics of cosmic inflation decades before the concept was invented. De Sitter spacetime represents the geometric foundation that makes inflation possible. Imagine you're standing still while space around you expands rapidly. There comes a point where distant objects get carried away so fast that their light can never reach you again. This invisible boundary is called an event horizon. It forms naturally around any observer in a rapidly expanding universe. Light from beyond this boundary gets trapped by the expansion of space itself. During inflation, every point in space develops its own event horizon. The exponential expansion creates these boundaries around all observers simultaneously. The event horizon doesn't represent a physical barrier. It's more like an information barrier. Events beyond this boundary become permanently inaccessible to observation. These horizons fundamentally alter what observers can know about the universe during inflation. How do you describe positions in a universe that's constantly expanding? Scientists use a clever trick called comoving coordinates. These coordinates expand along with space itself. Imagine drawing a grid on a balloon, then inflating the balloon. The grid lines stretch with the balloon's surface. That's exactly how comoving coordinates work during cosmic expansion. In this coordinate system, objects that aren't moving relative to the expansion appear to stay at fixed positions. Their comoving coordinates don't change, even though the physical distances between them grow enormously. This coordinate system makes it much easier to track how different physical quantities evolve during inflation. Densities, temperatures, and field values can be measured consistently throughout the expansion. Comoving coordinates provide the mathematical framework for understanding inflation physics. What happens to the actual distance between 2 points during inflation? Scientists call this the proper distance, and it grows at mind-bending rates. 2 points that start incredibly close together can end up separated by vast cosmic distances. the proper distance between them increases exponentially with time. This isn't because the points are moving through space. The space itself is expanding, carrying the points along with it. The distance grows because there's literally more space between them. During inflation, proper distances can increase by factors of 10 to the 30 or more. That's a 1 followed by 30 zeros. Regions that were once neighbors become separated by distances larger than galaxies. The exponential growth of proper distances transforms the cosmic landscape completely. Light gets stretched as it travels through expanding space. The wavelengths become longer, shifting toward the red end of the spectrum. Scientists call this cosmological redshift. During inflation, this stretching becomes extreme. Photons that start with high energy get stretched until they have almost no energy left. The expansion literally drains their power away. High-energy gamma rays can get redshifted all the way down to radio waves. The light doesn't disappear, but it becomes so stretched that it carries virtually no energy anymore. This process removes almost all radiation from the universe during inflation. By the end of the inflationary period, space becomes nearly empty of photons. The extreme redshift evolution clears the cosmic slate clean for what comes next. Empty space isn't actually empty. Quantum mechanics tells us that particle pairs constantly pop into existence and then annihilate each other. This happens everywhere, all the time. But during inflation, something remarkable occurs. The rapidly changing gravitational field can prevent these particle pairs from annihilating. Instead of disappearing, they become real, permanent particles. This process is called gravitational particle production. The expanding spacetime literally creates matter and energy from quantum vacuum fluctuations. The particles created this way carry information about the inflationary process. Their properties depend on how fast space was expanding and how the expansion rate changed over time. This quantum particle production connects the microscopic world of quantum mechanics to the macroscopic expansion of space. Einstein showed us that space and time are connected. During inflation, this connection becomes crucial for understanding how light travels through the expanding universe. Scientists use a special time coordinate called conformal time. In this coordinate system, light rays travel in perfectly straight lines just like they do in flat spacetime. This mathematical trick makes it much easier to calculate how light and particles behave during inflation. Complex curved paths become simple straight lines. Conformal time runs differently than ordinary time during inflation. What seems like enormous time intervals in ordinary coordinates can correspond to tiny intervals in conformal time. This time coordinate reveals the hidden simplicity underneath inflation's complex physics. Inflation fundamentally changes how different regions of space can influence each other. The rapid expansion alters the basic structure of cause and effect relationships. Before inflation, nearby regions could exchange light signals and influence each other. But exponential expansion stretches space so rapidly that causal contact gets broken. Regions that were once in causal contact become isolated. They're light cones which define what can influence what gets stretched beyond recognition. This causal disconnection explains why different parts of our observable universe can show identical properties. They were connected before inflation separated them. The reshaping of causal structure during inflation solves fundamental puzzles about cosmic uniformity. Inflation ends with the universe cold and nearly empty. The exponential expansion has diluted away almost all matter and radiation. Space contains mainly the inflaton field and its energy. But this can't last. The inflaton field becomes unstable and begins to decay. Its stored energy gets converted into ordinary particles and radiation through a process called reheating. These newly created particles interact with each other rapidly. Collisions and reactions quickly establish thermal equilibrium throughout space. The universe becomes hot and dense again. This thermalization process creates the initial conditions that standard Big Bang theory requires. The hot, dense state allows nuclear reactions to begin and the cosmic timeline to proceed normally. The reheating phase connects the end of inflation seamlessly to the beginning of conventional cosmic history. Empty space isn't really empty. This discovery shocked physicists when they first understood quantum mechanics. Even in perfect vacuum, tiny energy fluctuations appear and disappear constantly. These vacuum fluctuations arise from Heisenberg's uncertainty principle. This fundamental law of physics states that you can never know both energy and time with perfect precision. The more precisely you try to measure energy, the less precisely you can know when that measurement occurred. This uncertainty allows energy to briefly borrow from nothing and create particle pairs. These pairs appear spontaneously, exist for incredibly short moments, then annihilate each other and disappear. During inflation, these microscopic quantum fluctuations get stretched to macroscopic sizes. What starts as subatomic uncertainty becomes cosmic scale density variations that eventually form galaxies and stars. Vacuum fluctuations represent the quantum mechanical foundation for all large-scale structure in the universe. How do quantum fluctuations become real density variations in space? The answer lies in quantum field theory. This mathematical framework describes how quantum effects operate in expanding spacetime. Quantum field theory treats particles as excitations in underlying energy fields. These fields exist everywhere in space, and their quantum fluctuations create temporary particle-antiparticle pairs throughout the vacuum. During inflation, the rapidly changing gravitational field prevents these quantum pairs from annihilating normally. Instead of disappearing back into nothingness, they become permanent, real particles. This process is called particle production from the quantum vacuum. The inflaton field's quantum fluctuations get converted into density perturbations that survive after inflation ends. Quantum field theory provides the mechanism that transforms microscopic uncertainty into macroscopic cosmic structure. During inflation, quantum fluctuations start smaller than atoms but grow rapidly due to exponential expansion. There comes a crucial moment when their wavelengths become larger than the observable horizon. This transition is called horizon crossing. Before this moment, the fluctuations behave like quantum waves. After crossing, they become classical density perturbations that follow ordinary physics laws. The horizon during inflation represents the maximum distance over which causal influence can operate. Once fluctuation wavelengths exceed this distance, they freeze out and stop evolving quantum mechanically. This freezing process preserves the quantum fluctuations as permanent density variations. They maintain their amplitude and phase, creating the initial conditions needed for structure formation. Horizon crossing transforms ephemeral quantum uncertainty into lasting cosmic seeds. Measuring density fluctuations in expanding space presents a tricky problem. Different coordinate systems can make the same physical situation look different mathematically. Scientists need gauge invariant quantities. These are measurements that give the same answer regardless of which coordinate system you choose to use. Think of measuring the temperature in a room. The temperature value shouldn't depend on whether you use Celsius or Fahrenheit scales. Similarly, real physical density fluctuations shouldn't depend on your choice of cosmic coordinates. Gauge invariant perturbations represent the actual physical density variations that exist in space. These are the fluctuations that eventually grow under gravity to form galaxies and larger structures. Only gauge invariant quantities have real physical meaning in cosmological perturbation theory. Density fluctuations come in many different sizes. Some span tiny regions while others stretch across vast cosmic distances. Scientists need a way to measure how strong the fluctuations are at each different scale. This measurement is called the power spectrum. It shows the amplitude of density variations as a function of their wavelength or frequency. Imagine analyzing the sound from an orchestra. A power spectrum would show how much energy exists at each musical note. Similarly, the cosmological power spectrum shows how much density fluctuation exists at each cosmic scale. Inflation predicts a nearly flat power spectrum. This means fluctuations have similar strength across a wide range of scales, from galaxy-sized regions to much larger structures. The power spectrum provides the statistical description of primordial density fluctuations. Inflation produces fluctuations that look remarkably similar at different size scales. This property is called scale invariance, and it represents one of inflation's most striking predictions. Scale invariant fluctuations means the statistical properties remain the same whether you examine small regions or large regions. The patterns repeat across different scales like a fractal structure. This uniformity arises because inflation stretches quantum fluctuations that all originated from the same physical scale. The expansion process preserves their relative relationships across all the different scales they get stretched to. Without scale invariance, some cosmic scales would have much stronger fluctuations than others. We'd expect to see dramatic variations in structure density across different size ranges. Scale invariance explains why galaxies, galaxy groups, and galaxy clusters all show similar statistical clustering properties. The primordial fluctuations created during inflation have a special property. They affect all different types of matter and energy in exactly the same way. Scientists call these adiabatic perturbations. In regions where normal matter becomes slightly denser, dark matter also becomes denser by exactly the same percentage. Where radiation gets slightly more concentrated, everything else gets more concentrated proportionally. This synchronized behavior arises because inflation creates fluctuations in the space-time geometry itself. All forms of matter and energy respond identically to these geometric perturbations. Adiabatic perturbations contrast with isocurvature perturbations, where different components fluctuate independently. Inflation strongly suppresses isocurvature modes, predicting primarily adiabatic fluctuations. The adiabatic nature of primordial perturbations leaves distinctive signatures in the cosmic microwave background radiation. The density fluctuations created during inflation follow a specific statistical pattern. Most regions have density values very close to the average, with fewer and fewer regions having extreme high or low densities. This pattern is called a Gaussian distribution, also known as a normal distribution or bell curve. It's the same statistical pattern you see in many random processes in nature. Gaussian fluctuations arise naturally from quantum mechanics. When many independent quantum events combine together, the central limit theorem guarantees that their sum follows a Gaussian distribution. Inflation amplifies quantum fluctuations while preserving their Gaussian statistical properties. This creates a universe where most regions have typical densities, with rare regions being much denser or much emptier. Gaussian primordial fluctuations predict specific patterns in galaxy clustering and cosmic microwave background temperature variations. Inflation doesn't just create density fluctuations, it also produces gravitational waves that ripple through the fabric of spacetime itself. Scientists call these tensor mode perturbations. These primordial gravitational waves arise from quantum fluctuations in the gravitational field during inflation. Just like matter fields experience quantum uncertainty, space-time geometry itself fluctuates at quantum scales. Inflation stretches these gravitational field fluctuations to macroscopic wavelengths. The resulting gravitational waves propagate through space at light speed, carrying information about the inflationary epoch. Tensor modes create distinctive polarization patterns in the cosmic microwave background radiation. These B-mode polarization signatures represent one of the most sought-after confirmations of cosmic inflation. The amplitude of tensor modes depends on the energy scale of inflation, providing a direct probe of inflationary physics. The fluctuations created during inflation provide the initial conditions for everything that happens afterward in cosmic history. These quantum-generated density variations become the seeds from which all structure grows. After inflation ends, gravity begins amplifying these tiny density differences. Regions that started slightly denser attract more matter and become even denser over time. This gravitational amplification process eventually creates the cosmic web of galaxies, galaxy clusters, and vast empty voids that we observe today. Every galaxy traces its origin back to quantum fluctuations during inflation. The statistical properties of these initial fluctuations determine the final distribution of matter throughout the universe. Galaxy clustering, the sizes of cosmic voids, and the texture of large-scale structure all reflect the primordial fluctuation spectrum. Inflation's quantum fluctuations provide the cosmic DNA that determines the universe's large-scale architecture. Every point in space contains an invisible energy field. This field exists everywhere simultaneously. It has no direction, no spin, just pure energy value at each location. Scientists call this a scalar field. The word scalar means it has magnitude but no direction. Think of it like temperature in a room. Every point has a temperature value, but temperature itself doesn't point anywhere. The scalar field responsible for inflation is called the inflaton. This field permeates all of space uniformly. Its energy density remains constant from place to place during the inflationary period. Unlike electromagnetic fields that create light, or gravitational fields that create attraction, the inflaton field creates repulsive effects. Its uniform energy density drives the exponential expansion of space itself. This invisible scalar field represents the engine that powers cosmic inflation. The inflaton field can store energy in different ways. Just like a ball on a hill has potential energy that depends on its height, the inflaton field has potential energy that depends on its value. This potential energy function determines everything about inflation. When the field sits at high potential energy values, it drives rapid expansion. When it reaches lower values, inflation ends. The shape of this potential energy curve controls how long inflation lasts and how fast space expands. Different potential shapes create different inflationary scenarios. Think of the potential energy like a cosmic landscape with hills and valleys. The inflaton field rolls through this landscape, and its position determines the universe's behavior. This potential energy function provides the fundamental physics behind cosmic inflation. The inflaton field doesn't rush down its potential energy hill. Instead, it rolls slowly and gently. Scientists call this the slow roll condition. This slow motion is crucial for sustained inflation. If the field moved too quickly, inflation would end almost immediately. The gradual descent allows exponential expansion to continue for many foldings. What keeps the field moving slowly? The expansion of space itself creates a friction-like effect. This cosmic friction prevents the field from accelerating rapidly down the potential. During slow roll, the field's kinetic energy remains much smaller than its potential energy. The potential energy dominates, driving the repulsive expansion that characterizes inflation. This gentle slow roll motion sustains the inflationary epoch for the duration needed to solve cosmic problems. Every type of matter and energy has a pressure-to-density ratio. This ratio determines whether the substance creates gravitational attraction or repulsion. Normal matter has positive pressure, but the ratio stays between 0 and 1/3. This creates ordinary gravitational attraction that pulls things together. But the inflaton field has a very different ratio. Its pressure-to-density ratio equals -1. This negative pressure creates gravitational repulsion instead of attraction. Scientists call this relationship the equation of state. When this ratio equals -1, Einstein's equations demand exponential expansion of space. This unusual equation of state transforms the inflaton field into a cosmic repulsive force. How does the inflaton field change over time? Its evolution follows a specific mathematical equation discovered by physicists Klein and Gordon. This equation describes how scalar fields behave in curved spacetime. It combines quantum mechanics with general relativity to predict the field's motion through its potential energy landscape. The Klein-Gordon equation includes terms for the field's acceleration, the cosmic expansion, and the slope of the potential energy function. All these factors work together to determine how the field evolves. During inflation, this equation shows why the field moves slowly down its potential. The expansion of space creates additional terms that act like friction, slowing the field's motion. The Klein-Gordon equation provides the mathematical foundation for understanding inflaton field dynamics. Why doesn't the inflaton field just race quickly down its potential energy hill? The expansion of the universe itself creates a braking effect. This cosmic friction appears as a damping term in the field's equation of motion. The faster the universe expands, the stronger this damping becomes. But think of trying to move quickly through thick honey. The honey creates resistance that slows your motion. Cosmic expansion creates similar resistance for the inflaton field. This damping term has a coefficient that equals 3 times the Hubble parameter. During inflation, this becomes a large number that significantly slows the field's evolution. Without this cosmic friction, inflation would end too quickly to solve the horizon and flatness problems. Inflation cannot continue forever. At some point, the inflaton field must transition from its high-energy state to a lower-energy configuration. This transition represents a phase change in the fundamental structure of space itself. Scientists call this process symmetry breaking. It's like water freezing into ice, but much more dramatic. During symmetry breaking, the inflaton field rolls rapidly toward the bottom of its potential energy valley. This rapid motion ends the slow roll conditions that sustain inflation. The field's stored potential energy gets converted into kinetic energy and then into ordinary particles and radiation. This conversion process creates the hot, dense conditions needed for Big Bang nucleosynthesis. Symmetry breaking provides the natural mechanism that terminates cosmic inflation. Even during inflation, the inflaton field experiences tiny quantum vibrations. These microscopic fluctuations get amplified by the exponential expansion of space. What starts as quantum uncertainty at subatomic scales grows into macroscopic density variations spanning vast cosmic distances. These field excitations become the seeds for all future structure formation. The fluctuations have two components. Scalar perturbations create density variations that eventually form galaxies and galaxy clusters. Tensor perturbations create gravitational waves that ripple through spacetime itself. These quantum excitations preserve information about the inflationary process. Their statistical properties depend on how fast space expanded and how the expansion rate changed over time. Field excitations connect the microscopic quantum world to the macroscopic structure of the universe. The simple potential energy function we've discussed gets modified by quantum effects. Virtual particles constantly pop in and out of existence, altering the field's behavior. Scientists call the modified version the effective potential. This includes all the quantum corrections that arise from particle interactions and quantum loop effects. These quantum corrections can significantly change the potential's shape. They might create new minima, alter the slopes, or add oscillations to the smooth classical potential. The effective potential determines the actual physics of inflation. Predictions about density fluctuations and gravitational waves depend on this quantum-corrected version, not the simple classical potential. Understanding the effective potential requires sophisticated calculations that combine quantum field theory with cosmic expansion. When inflation ends, the universe becomes cold and nearly empty. The inflaton field contains enormous stored energy, but space lacks the particles and radiation that normal cosmology requires. This energy must be converted into ordinary matter and radiation through a process called reheating. The inflaton field becomes unstable and begins to decay into standard model particles. These decay products interact with each other through collisions and reactions. The interactions quickly establish thermal equilibrium throughout space, creating a hot, dense plasma. The reheating temperature determines which particles can be produced and what nuclear reactions can occur. This temperature must be high enough to allow Big Bang nucleosynthesis to proceed normally. Reheating completes the transition from the inflationary epoch to conventional cosmic evolution. Real inflation might involve more than just a single inflaton field. Multiple scalar fields could participate simultaneously in driving cosmic expansion. These multi-field scenarios create much richer dynamics. The fields can interact with each other, creating complex trajectories through multidimensional potential energy landscapes. Some fields might drive inflation while others remain dormant. Field interactions can trigger phase transitions that end inflation or modify the expansion rate during the inflationary epoch. Multi-field inflation can produce more complex patterns of density fluctuations and gravitational waves. The resulting signatures might be detectable in cosmic microwave background observations. Multiple field scenarios represent the cutting edge of modern inflationary theory, connecting cosmic inflation to advanced particle physics models. A NASA satellite called CUBI changed cosmology forever in the early 1990s. CUBI stands for Cosmic Background Explorer. This spacecraft was designed to map the temperature of ancient radiation that fills all of space. Scientists expected to find a perfectly uniform temperature everywhere they looked. Instead, Kobe discovered tiny temperature variations across the sky. These variations were incredibly small, less than 1 part in 100,000. But these microscopic temperature differences represented something monumental. They showed the first evidence of density fluctuations in the early universe. These are exactly the fluctuations that inflation theory predicted. The QOB team measured temperatures that varied by only about 10 millionths of a degree across different regions of the sky. Yet these tiny variations matched the theoretical predictions of cosmic inflation with stunning accuracy. This discovery provided the first direct observational evidence that inflation's quantum fluctuations really did seed all cosmic structure. How do you analyze temperature patterns across the entire sky? Scientists use a mathematical technique called the angular correlation function. This tool measures how temperatures at different angular separations are related to each other. Think of taking 2 thermometers and placing them at different positions in the sky. The correlation function tells you how likely those thermometers are to read similar temperatures based on how far apart they are. If the sky were completely random, there would be no correlation between distant regions. But inflation predicts specific correlation patterns that depend on the physical processes that created the fluctuations. The angular correlation function revealed that nearby regions on the sky tend to have similar temperatures, while very distant regions show little correlation. This pattern perfectly matches what inflation theory predicts. This mathematical analysis transformed random-looking temperature variations into clear evidence for inflationary physics. The temperature pattern across the entire sky contains an enormous amount of information. Scientists need a way to break this complex pattern down into simpler mathematical pieces they can analyze. They use a technique called multipole expansion. This method decomposes the sky pattern using spherical harmonics, which are mathematical functions that describe patterns on spherical surfaces. Think of analyzing a musical symphony by breaking it down into individual notes and harmonies. Multipole expansion does the same thing for cosmic temperature patterns, separating them into different angular scales and amplitudes. Each multipole moment corresponds to a different angular scale on the sky. Low multipoles represent large-scale patterns, while high multipoles capture small-scale details. This mathematical decomposition allows scientists to compare observations directly with theoretical predictions from different inflation models. Before atoms formed, the early universe contained a hot plasma of charged particles and photons. This plasma could support sound waves, just like air supports sound waves in our atmosphere. These cosmic sound waves created pressure oscillations in the plasma. Regions of high density compressed and rarefied in regular cycles, creating acoustic oscillations throughout the early universe. When atoms finally formed and the plasma cleared, these sound waves left their signature frozen in the temperature patterns of the cosmic microwave background. Scientists call these signatures acoustic peaks. The acoustic peaks appear as distinctive bumps in the multipole power spectrum. Their positions and heights depend on the fundamental parameters of the universe, including the effects of inflation. These acoustic signatures provide precise measurements of cosmic geometry and confirm that inflation set up the initial conditions for these oscillations. Density fluctuations come in many different sizes, from small regions to vast cosmic scales. The spectral index measures how the strength of these fluctuations changes as you look at different size scales. A spectral index of exactly 1 would mean all scales have identical fluctuation strength. Values slightly less than 1 indicate that large scales have slightly stronger fluctuations than small scales. Inflation predicts a spectral index very close to, but not exactly equal to 1. The tiny deviation from perfect scale invariance depends on the specific details of the inflationary process. Precise measurements show the spectral index equals approximately 0.96. This value perfectly matches the predictions of simple inflation models and rules out many alternative theories. The spectral index provides one of the most stringent tests of inflation theory available from current observations. The Wilkinson microwave anisotropy probe, known as BUM-AP, represented a huge leap forward in precision cosmology. Launched in 2001, this satellite could measure cosmic temperatures far more accurately than any previous instrument. BUM-AP observed the cosmic microwave background for 9 years, creating the most detailed temperature maps of the early universe ever produced. The mission could detect temperature variations as small as millionths of a degree. These ultra-precise measurements allowed scientists to determine the fundamental parameters of inflation with unprecedented accuracy. BUM-AP confirmed that the universe is flat, that density fluctuations are nearly scale invariant, and that they follow Gaussian statistics. The BUM-AP results eliminated many alternative theories to inflation while confirming inflation's key predictions. The data showed that simple inflation models could explain observations with remarkable precision. BUM-AP transformed inflation from a promising idea into the standard model of the very early universe. The European Space Agency's Planck satellite achieved the ultimate precision in cosmic microwave background measurements. Launched in 2009, Planck could measure temperatures and polarizations with sensitivity limits approaching theoretical maximums. Planck mapped the entire sky with angular resolution 3 times better than a BUM-AP and sensitivity 10 times greater. This allowed scientists to detect subtle features in the temperature patterns that previous missions couldn't resolve. The Planck data provided the most stringent tests of inflation theory ever conducted. The satellite confirmed that primordial fluctuations are indeed Gaussian, nearly scale invariant, and adiabatic. Most importantly, Planck placed tight constraints on alternative inflation models. Many theoretically possible inflation scenarios were ruled out by the precision of Planck's measurements. Planck's observations represent the pinnacle of cosmic microwave background science and provide the definitive confirmation of basic inflation predictions. Light waves can vibrate in different directions as they travel through space. This property is called polarization. The cosmic microwave background photons should also be polarized if primordial gravitational waves existed during inflation. Gravitational waves stretch and squeeze space in specific patterns. These distortions would create distinctive polarization signatures in the cosmic microwave background called B-mode patterns. Detecting B-mode polarization represents one of the holy grails of modern cosmology. This signal would provide direct evidence for the gravitational waves that inflation theory predicts should be generated during exponential expansion. Several ground-based and balloon-borne experiments are searching for these elusive B-mode signals. The amplitude of this polarization depends directly on the energy scale at which inflation occurred. B-mode polarization detection would confirm one of inflation's most distinctive predictions and open a direct window into the physics of the very early universe. Inflation predicts that primordial fluctuations should follow Gaussian statistics. This means the temperature variations should be perfectly random, with no special patterns or correlations beyond what pure chance would create. but some inflation models predict small deviations from perfect Gaussianity. These non-Gaussian signatures would appear as subtle correlations between temperature fluctuations at different locations and scales. Scientists have developed sophisticated statistical tests to search for non-Gaussian patterns in the cosmic microwave background data. These tests can detect extremely small deviations from perfect randomness. Current observations show that primordial fluctuations are consistent with Gaussian statistics within measurement uncertainties. This rules out many exotic inflation models that would produce significant non-Gaussianity. The Gaussian nature of cosmic fluctuations supports simple, single-field inflation models while constraining more complex theoretical scenarios. The spectral index measures how fluctuation strength changes with scale, but some inflation models predict that the spectral index itself should change slightly as you examine different scales. This change is called the running of the spectral index. It represents a second-order effect where the slope of the power spectrum itself has a slight curvature rather than being perfectly straight. Running would appear as a gentle bending in the power spectrum when plotted on a logarithmic scale. The amount of running depends on the specific dynamics of the inflaton field during inflation. Current observations place tight limits on any possible running of the spectral index. The measurements are consistent with zero running, supporting simple inflation models with minimal field dynamics. The absence of detectable running eliminates many complex inflation scenarios while favoring straightforward single-field models. Not all primordial fluctuations need to be adiabatic. Some theoretical models predict isocurvature modes, where different types of matter fluctuate independently rather than together. In isocurvature fluctuations, regions where normal matter becomes denser might have less dark matter, or areas with more radiation could have fewer particles. These fluctuations affect the ratios between different components rather than the total density. Inflation strongly suppresses isocurvature modes while amplifying adiabatic ones. This happens because inflation creates fluctuations in spacetime geometry itself, which affects all matter types equally. Observations show that primordial fluctuations are almost entirely adiabatic, with very little contribution from isocurvature modes. This provides strong support for the inflation paradigm. The dominance of adiabatic over isocurvature fluctuations represents another successful prediction that distinguishes inflation from alternative early universe scenarios. Inflation produces both density fluctuations and gravitational waves. The relative strength of these two types of fluctuations is called the tensor-to-scalar ratio, often denoted as the parameter r. This ratio directly measures the energy scale at which inflation occurred. Higher energy inflation produces stronger gravitational waves relative to density fluctuations, giving a larger value of r. Current observations place an upper limit on r of approximately 0.06. This means gravitational waves contribute less than 6% as much as density fluctuations to temperature variations in the cosmic microwave background. This constraint implies that inflation occurred at energy scales far below the Planck scale, where quantum gravity effects become important. It favors low-energy inflation models over high-energy scenarios. Future B-mode polarization experiments aim to detect the gravitational wave signal and measure r precisely, providing direct information about the energy scale of cosmic inflation. Inflation might never completely end everywhere in space. While it stops in some regions like our observable universe, it could continue forever in other areas, creating an endless process of cosmic creation. This concept is called eternal inflation, once inflation begins anywhere. Quantum fluctuations ensure that it keeps restarting in new regions of space even after it ends in others. Think of it like a forest fire that keeps spreading to new areas even as firefighters extinguish it in other locations. Some patches of space-time continue inflating while others transition to normal cosmic evolution. Each region that stops inflating becomes a separate universe with its own Big Bang-like beginning. These bubble universes expand within the eternally inflating background space-time. Eternal inflation suggests that our universe is just one bubble among infinitely many others, all embedded in an ever-expanding multiverse structure. What if our universe is just one among countless others? The multiverse concept proposes that infinite numbers of separate universes exist simultaneously, each with potentially different laws of physics. These universes don't interact with each other directly. They exist as separate space-time regions that can't exchange information or influence each other's evolution. Each universe in this vast ensemble might have different fundamental constants, different particle types, or even different numbers of spatial dimensions. Most would be lifeless and empty, but some might harbor complexity in life. This idea challenges our understanding of what makes our universe special. Instead of requiring fine-tuning to explain life-friendly conditions, the multiverse provides infinite attempts to get the combination right. The multiverse concept transforms cosmology from studying the universe to studying the ensemble of all possible universes. String theory proposes that fundamental particles aren't point-like objects, but tiny vibrating strings existing in multiple dimensions beyond the three spatial dimensions we experience. This theory naturally incorporates inflation through the dynamics of these higher dimensional spaces. Extra dimensions can undergo their own expansion phases, driving inflation in our observed three-dimensional space. String theory also predicts the existence of scalar fields similar to the inflaton. These fields arise from the geometry of the extra dimensions and can create the potential energy landscapes needed for inflation. The theory suggests that inflation might be a generic consequence of string physics rather than a special fine-tuned process. Different string configurations could produce different types of inflationary scenarios. String theory provides a fundamental framework that could explain why inflation occurs and predict its observable consequences. String theory doesn't predict a unique universe. Instead, it allows for an enormous number of different possible solutions, each corresponding to a different way of arranging the extra dimensions. Scientists call this vast collection of possibilities the string landscape. Current estimates suggest there might be 10 to the 500 different possible universes that string theory allows. This creates a major problem for making testable predictions. With so many possibilities, how can we determine which solution corresponds to our actual universe? The landscape problem has transformed the question from why does our universe have these properties, to how do we find our universe among all the possibilities that string theory permits. This mathematical abundance presents both a challenge and an opportunity for understanding the fundamental nature of reality. How do you calculate probabilities when dealing with infinite quantities? This seemingly simple question creates one of the deepest puzzles in multiverse cosmology. In eternal inflation, every possible event happens infinitely many times across the infinite expanse of space-time. This makes it impossible to define meaningful probabilities using standard mathematical methods. For example, If both rare and common events occur infinitely often, how do you determine which is more likely? The usual rules of probability theory break down completely. Different methods of counting or measuring infinite sets give different answers to the same probability questions. This ambiguity undermines our ability to make testable predictions about multiverse scenarios. The measure problem represents a fundamental mathematical challenge that must be solved before multiverse theories can make definitive predictions. Our universe is currently undergoing accelerated expansion, driven by mysterious dark energy that makes up about 70% of the total energy density in space. This modern acceleration might be related to the same physics that drove inflation in the early universe. Both processes involve the universe expanding at an accelerating rate due to unusual forms of energy. Some theories propose that dark energy represents a very weak continuation of the inflationary process. The same types of scalar fields that drove early inflation might still be active today. Alternatively, dark energy and inflation might arise from different aspects of the same underlying physics. Understanding one process could provide crucial insights into the other. The connection between early inflation and current acceleration represents one of the most intriguing puzzles in modern cosmology. The density fluctuations created during inflation were usually tiny, but in rare regions. These fluctuations might have been large enough to create black holes directly from compressed matter. These primordial black holes would form much earlier than the stellar black holes created by collapsing stars. They could have a wide range of masses, from microscopic to stellar scales. Small primordial black holes would evaporate quickly through Hawking radiation. Larger ones could survive to the present day and contribute to the mysterious dark matter that fills our universe. The abundance and mass distribution of primordial black holes depends sensitively on the details of inflation and the spectrum of density fluctuations it produced. Detecting primordial black holes would provide a direct probe of the extreme density fluctuations that occurred during cosmic inflation. At incredibly small scales approaching the Planck length, our current theories of physics break down. Quantum mechanics and general relativity become incompatible, requiring a new theory of quantum gravity. These quantum gravity effects might significantly modify inflation when the universe much smaller than it is today. The exponential expansion during inflation could stretch quantum gravity signatures to observable scales. Different approaches to quantum gravity, such as loop quantum gravity or causal set theory, make different predictions about how inflation should be modified at the Planck scale. These modifications could leave distinctive signatures in the cosmic microwave background radiation or the spectrum of gravitational waves produced during inflation. Understanding quantum gravity represents the key to unlocking the ultimate physics of the inflationary epoch. Future observations will push the tests of inflation theory to their ultimate limits. New telescopes and detectors are being designed to search for the subtle signals that inflation theory predicts. Ground-based and space-based experiments will search for the elusive B-mode polarization that primordial gravitational waves should create. These measurements could determine the energy scale at which inflation occurred. Advanced galaxy surveys will map the three-dimensional distribution of matter across cosmic history, testing inflation's predictions about structure formation on the largest scales. Gravitational wave detectors might eventually become sensitive enough to detect the primordial gravitational wave background that inflation should have created. These next-generation observations will either confirm inflation's remaining predictions or reveal new physics that requires modifications to the basic inflationary paradigm. Not all cosmologists accept inflation as the solution to early universe problems. Several alternative theories attempt to explain cosmic uniformity and flatness without requiring an inflationary epoch. Cyclic cosmology proposes that the universe goes through repeated cycles of expansion and contraction. Each cycle resets the initial conditions and could explain why the universe appears uniform and flat. Bouncing cosmology suggests that the Big Bang was preceded by a contracting phase. The bounce from contraction to expansion could create the observed cosmic properties without inflation. Other alternatives involve modifications to gravity or the introduction of novel forms of matter and energy in the early universe. Each proposes different mechanisms to solve the problems that inflation addresses. These alternative theories provide important tests of inflation by offering competing explanations for the same observational evidence.